Okay, let's continue our discussion. We are still on coordinate transformation. Now we move on to transformation from local to global coordinate system. So now we are going to consider transformation of member end forces and end displacement from local to global coordinate system. So what we're going to do, same procedure, we're going to consider again figure B and figure C that we have shown a while ago. We're going now to get the x and y component for the local coordinate system for each member. So if we're going to have the transformation of the local coordinate system to global coordinate system, we can have this equation. We have now the equation for F1, F2, F sub 3, and F sub 4. This equation can be written in matrix form. So this is the equation in matrix form. Of course, this is per member. So as mentioned, for every member, there would be 4 end forces in the local and global coordinate system. So for every member, you are going to have F1, F2, F3, F sub 4 is equal to, you have now the transformation matrix equal to Q1 multiplied to Q1, Q2, Q3, and Q sub 4. So if you're going to have the equation now for the transformation from local to global coordinate system, this is now the simplified equation. You have F is equal to the transpose of the transformation matrix. What is the transpose of transformation matrix? Of course, you're going to get the value for the transformation matrix, the equation that we have introduced a while ago. You're going to use that one. Then get the transpose, meaning to say the vertical direction will now be the horizontal. The column will now be, the number of column will be equivalent now to the number of rows, meaning to say if we're going to have the transpose of the transformation matrix, the placement of the elements will be from column, it will now be equivalent to rows. So first column will now equivalent to the first row, second column will be equivalent now to the second row, third column will be the equivalent now for the third row, and so on. So that is the value for the transpose of the transformation matrix. So you can, this is now the equation for our transformation from local to global coordinate system. So if you're going now to transform end displacement from local to global coordinate system, you have this equation. Of course, V is equal to the transpose of the transformation matrix multiplied to our U, which is our end displacement in the local coordinate system. So we have transformed our local end displacement to global end displacement. So this equations, of course, is for every member. So if there would be 8 members, meaning to say you're going to have the value for this member end forces in the global and member end displacement in the global, solving for 8 equations. For example, if that would be member 1, you are going to have F sub 1 equal to the transpose of the transformation matrix for member 1 multiplied to Q sub 1, similar to Q sub 2. So this is per member. So that is for the transformation from local to global coordinate system. So if we're going to apply those equations to our example, you have here an example. Number 1, you just have to determine the transformation matrix of the members. So for this, if you're going to, you have given with the figure, you have 6 members for the places. So what you're going to do, just use the formula for our transformation matrix. So the transformation matrix, you're going to identify, as mentioned a while ago, the value for cosine theta and sine theta. Whatever is the value for every member. For a member 1, get the value for cosine theta, sine theta. For member 2, 3, 4, and 5, and 6. Then afterwards, once you have identified the value for cosine theta and sine theta, you simply have to substitute to our transformation matrix. Then afterwards, that will be now the value for transformation matrix for each member. So we have solved that one. Okay, let's move on to sample number 2. Example number 2 is you're given with this figure. You're going with a member end displacement for member 2 in the global coordinate system. So this is member 2. You're given with end displacement for member 2 in the global coordinate system. So we have here the value which is written in matrix form, 0.75, 0, 1.5, -2 inches. So this 2 is at the beginning of the member, 3 and 4 is at the end of the member. What is being asked on the problem? You're going to compute for the end forces for member 2 in the global coordinate system, and you're going to check if the forces are in equilibrium. So how do we obtain the the global coordinate system for the member end forces? So we start with so this is the illustration. We just draw and identify the end displacement in the global coordinate system for member 2. Then for our solution, we simply have to get the value for K, our stiffness coefficient in the local coordinate system. So simplify that one. Of course, you get the value of E, and L. E, modulus of elasticity, A, area, and L is your the value for the length of our member. So if you're going to have now the stiffness coefficient in for our member 2, so this is now the equation for the stiffness coefficient for member 2. Then afterwards, you get the transformation matrix. So for transformation matrix, you simply have to use the transformation matrix equation, get the value for cosine theta, and of course for sine theta. Then afterwards, once you have that one, this is now the equation for transformation matrix for member 2. Then after that, we can get now the member end displacement in the local coordinate system. So of course, U sub 2 is equal to K multiplied to our V. So once you simplify this one, so you have now the simplified form. This is the value for U1, U2, U3, and U sub 4 for member 2. Then afterwards, you're going to get now the member end forces in the local coordinate system. You simply have to use the equation Q is equal to K times U. You simply have to substitute the value for K, substitute the value for U, and simplify that one, operations of matrices. And you have now the value for our Q1, Q2, Q3, Q sub 4 for member 2. Once we obtain the member end forces in the local coordinate system, we can now transform our local coordinate system to global coordinate system using this equation. F is equal to the transpose of transformation matrix multiplied to Q. Of course, you have now the equation, the value for transformation matrix, get the transpose of that, and multiply to our member end forces in the local coordinate system. We have this value, simplify this one through operations of matrices equal to, you have F1, 345, F2, 460, F sub 3, negative 345, and F sub 4s, negative 460, which is in kips. So this is now the unknown data that was asked in the question to solve for member end forces in the global coordinate system. So you're going to check if the forces are in equilibrium. So to check this one, you simply have to make use of the three equations of equilibrium: summation of x forces equal to 0, summation of F equal to 0, and summation of moment equal to 0 for member 2. So as upon checking, so it is equal, all of those are equal to 0, so meaning to say the member is in equilibrium. So meaning to say member 2 is in equilibrium. So that ends for our discussion for coordinate transformation.